So a matrix is an array of numbers, and there's going to be rows and columns of numbers. It's kind of going to be like a table of numbers. I know I said this earlier in the semester too. But like this is my matrix capital A. Usually I use capital letters to represent matrices. And so this matrix has 2 rows and 2 columns. And if I write lowercase a 1 comma 2, what I'm trying to indicate with this kind of notation is tell me the entry in the matrix that lives in row 1, column 2. And so row 1, column 2 would be the number 6. And if I ask you about a2 comma 1, that subscript is telling me look in row 2, column 1, and so that would be 7. If I write something like this, like a with subscript 1, that's telling me, give me the vector of all the entries in row 1. So a subscript 1 is going to be the vector 5, 6. If instead I gave you this vector, this notation, where I have a little colon in the subscript, comma 1, this is saying, give me a vector that contains all of the rows, but only in column 1. And so this would be the vector 5, 7. So in the subscript, my personal convention is that I do row, comma, column. If I just give you one number in the subscript, I'm telling you what row I'm looking at. And if I give you a colon, comma, a number, I'm telling you which column to look at. And it's been a little bit since I actually programmed anything in Python, but if I remember correctly, that's also the convention that like Python uses. So if you're using Python to code with arrays and you do a colon, it tells Python to actually consider all of those rows for a particular column.
Oh, yeah. So 2 columns would be the whole matrix.
Yeah. So if I wrote a colon comma 2, that would be the vector 6, 8. But a2 would be the vector 7, 8. Okay. So if we have a matrix A, and the matrix A has rows that are A1, A2, A3. So this is like a 3 by 3 matrix where there's 3 rows and 3 columns. And then I have a vector V, and my vector V, just has 3 entries, V1, V2, V3. Then if I want to multiply A times V, then we're going to define matrix vector multiplication to be this, where the product of the multiplication is a vector, and all of the entries in this vector are dot products. It's going to be the dot product between the rows of the matrix and the vector. So if I wanted to really expand this out, this is, again, the product is a vector. Matrix vector multiplication has a vector as a product. And if I write A1 dot V, what that's saying is take the entry in the matrix A1 comma 1 and multiply that times V1. That's just a scalar times a scalar, so that's not even a dot product. Plus, take the entry A1 comma 2 and multiply that times V2, plus A1 comma 3 and multiply that times V3. And then in the second row you do A2 comma 1 V1 plus A2 comma 2 V2 plus A2, comma 3, V3, and then so on for the third row. This is probably actually easier if I just show you an example, rather than just trying to explain it to death. So if I have the matrix M as 1, 1, 0, 1, and then the vector U is 3, 4, then the matrix vector multiplication M times U is going to be a 2-entry vector with size 2, where the first entry in this vector is going to be 1 times 3 plus 1 times 4, and then the second entry is going to be 0 times 3 plus 1 times 4. So the entries in the product vector are just the dot products of the rows of the matrix with the vector U. And so this vector is going to be 7, 4. I should have put some entries in this vector over here. So let's make this the vector 2, 3, 1. Nah, there's too many 2s and 3s and 1s over there. Let's make it 5, 7, 10. Oops. So if I'm looking at the matrix N and the vector A, then the matrix vector product N times A is going to be a vector with 3 entries, and the first is going to be 1 times 5 plus 0 times 7 plus 0 times 10. And then the next entry is going to be 1 times 5 plus 2 times 7 plus 0 times 10. And then the third entry is going to be 1 times 5 plus 2 times 7 plus 3 times 10. So altogether, the matrix vector product is going to be 5, 19, 49. This matrix B over here is what I would call a 2 by 3 matrix because it has 2 rows and 3 columns. And I can still multiply this B matrix times this V vector. The matrix vector product is going to be a vector with 2 entries. And so it's going to be 4 times 1 plus 5 times 1 plus 6 times negative 1 for the first entry. And then for the second entry, it'll be negative 4 times 1 plus negative 5 times 1 plus negative 6 times negative 1. And I want to point out that this vector 1, 1, negative 1 is where those 1s, these negative 1s come from, right? And then the green numbers come from the matrix. So 4 plus 5 minus 6 is going to be 3. And then this should just be the negative 3 then. Or do you guys feel like this is making sense, this matrix vector multiplication stuff? Okay. I could also multiply this, which is a 3 by 2 matrix, 3 rows and 2 columns, times a vector of size 2, in which case the product vector is going to be a vector with 3 entries, where it's going to be 1 times 4 plus 0 times negative 3, negative 1 times 4 plus 1 times negative 3, and then negative 1 times 4 plus 2 times negative 3. And so that's going to be 4, negative 7, and then negative 10, I think. If I did that right. And so, I said this before, I'm just going to repeat myself. Matrix vector multiplication means you take the dot products of the rows of the matrix with that vector, and it gives you the entries in your product vector. Every entry of the product vector is just a dot product between the rows of the matrix and the vector. And so, since that's the definition of how we're doing things, this is super important that whenever I have matrix vector multiplication, like I have a matrix A times some vector X, then the number of rows in this matrix A has to be equal to the number of entries in my vector. So like if A is a 4 by 5 matrix, and I want to multiply times a vector to do matrix vector multiplication, that means this vector has to be size 5. Oh shoot, I think I actually, this is completely wrong, hold on. That should be columns. That's important. My bad. So the number of columns in my matrix has to be equal to the number of entries in my vector. So if I have a 4 by 5 matrix, meaning I have 4 rows and 5 columns in my matrix, then I have to have a vector with 5 entries. Because if I'm going to do the dot product between two vectors, then the vectors have to have the same number of entries. And since I'm doing the dot product of the rows of the matrix with the vector, then there has to be the same number of elements or entries in every row of the matrix as there are entries in the vector, which means I have to have the same number of columns in the matrix as entries in the vector. And we can go through my examples and see that's what happened, right? So I have 2 columns here, and so I have a 2-entry vector. I have 3 columns here, and so I had to have 3 entries in my vector for that to work. I had 3 columns here, and so I had to have 3 entries in my vector. And then here I had 2 columns, and so I had 2 entries in this vector. If I tried to do something that didn't fit this requirement, like if I tried to do something like a matrix with 3 columns times a vector with just 2 entries, then this is not defined, right? Because again, what I'm trying to do is take the dot product of 1, 2, 3 with the vector 1, -1, and that's just not the same number of entries, so I can't do the dot product, and so that doesn't work. Now, if I have an equation where capital A is a matrix and X and B are both vectors, then this is what we call a matrix vector equation. So if you know the matrix A and the vector X, then solving for B just requires what we were calling matrix vector multiplication. You just have to do matrix vector multiplication to the matrix A and the vector X. If A and B are known, then solving for X is going to require what we did yesterday. If you want to solve for X in the matrix vector equation, then you have to do Gaussian elimination. I'll try to show you why. You know, if I have a matrix that is, let's say this matrix C1, C2, C3, C4, C5, C6, C7, C8, C9. Those are the entries in my 3 by 3 matrix. And then I have a vector x, y, z. So x, y, and z are just entries in this size 3 vector. And then this is equal to another vector ABC. What the matrix vector multiplication does here is it says C1x plus C2y plus C3z is the first entry in this vector. C4x plus C5y plus C6z is the second entry in this vector. And then C7x plus C8y plus C9z is the third entry in this vector. And so what we're saying is that this vector of size 3 that I got by doing matrix vector multiplication, this vector of size 3 is equal to this vector of size 3. And these vectors are only equal to each other if all three of their entries are equal to each other. And so I could instead take away these brackets and say that this entry has to be equal to A, this entry has to be equal to B, and this entry has to be equal to C. But now I have a system of 3 linear equations with 3 unknowns that I'm trying to solve for, x, y, and z. And so what we were doing yesterday is we were using Gaussian elimination to solve for x, y, and z. And so, again, this is just formulating the same problem 2 different ways. But if I have the matrix vector equation ax equals b, and we know a and b, and we want to solve for x, then what we're going to do is we're going to write the augmented matrix A augmented with B, and then after performing the Gaussian elimination algorithm, we're going to end up with, I'll explain this more in a minute, we're going to end up with the identity matrix augmented with x. So that last column, after we perform Gaussian elimination, that's where we read off our answers. It's because we were solving for x, and so our answers, the x vector, is going to appear in the farthest right column. So this notation right here, where I use the square brackets and then a vertical bar, is a matrix augmented with a vector. And so the vertical bar means augmented with. So A augmented with B means I have some matrix A with all these entries sorry, A31, A32, A33. Okay, so those are all 9 entries in my 3x3 matrix A. And I'm augmenting it with the vector B. And so the vector B has to have 3 entries, B1, B2, B3. So this is what we call an augmented matrix. It's the matrix A augmented with B. And again, this is just another way of restating what Gaussian elimination does. Gaussian elimination solves a matrix vector equation of this form for this vector x. So we've just talked about matrix vector multiplication. We could also do matrix matrix multiplication. And matrix matrix multiplication is, ooh, and there's another typo. This should be a B. But matrix, gosh, there's another typo. matrix multiplication is where you take two matrices. In this case, I've named them capital A, a matrix, times capital B, a matrix. And then what you end up with as a product is also a matrix. The entries in our product is going to be the dot products of the rows of the left matrix. In other words, the rows of A dotted with the columns of B. And since I'm dotting the rows of A with the columns of B, that means that matrix multiplication is not commutative. So if I write the matrix A times the matrix B, that gives me some product matrix. And if I write the matrix B times the matrix A, that gives me another product matrix. And these are not the same. So this is not commutative multiplication, which is weird because normally multiplication is commutative. Normally you can say 3 times 5 equals 5 times 3. But in the case of multiplying matrices, it is not commutative. Let me do some examples using Excel so I don't actually have to do all the multiplying by hand. But let's say I've got this matrix. I'm going to name it capital A. So that's my A matrix. And then I'm also going to have a B matrix. Oops. And if I want to find the product A times B, so I'm left multiplying by A, you could say I'm right multiplying by B. What I'm going to do in Excel is I'm going to type in equals and then MMULT, so that's short for matrix multiplication, open parentheses, and then I select the first matrix, and then comma, and then I select the second matrix. I close parentheses, and then I'm going to hold Control Shift Enter, and then it's just going to give me a number, and then I have to select a 3 by 3 region, and then click on the formula bar again, and then hold Control Shift Enter again, and then it'll actually do it right. So Excel is kind of clunky sometimes. But this is the product A times B with matrix multiplication. It's nice that Excel does it really fast, so I don't have to hand compute 9 dot products. If I want the product B times A, same thing, I type in equals MMULT for matrix multiplication. This time I select B first, comma, and then select A, and then I hit Enter, and then I select the 3 by 3 region here, and then Control Shift Enter, and then it gives me another matrix product. But notice that these are not the same, and the order of matrix multiplication really does matter. Okay. So by the way, if you wanted to multiply this matrix B times a vector V, and the vector V is 1, 1, negative 1, we'll say. So then BV, to do matrix vector multiplication in Excel, you use the same formula. It's still MMULT for matrix multiplication. Then we're going to select the B matrix, comma, the V vector, hit Enter. Then you select the 1 by 3 region to get the BV matrix vector product in Excel.
So you need to know advance the size of the result.
Well, yeah. The other thing too is that I told you that this doesn't work if the number of columns in the matrix doesn't match the number of entries in the vector, right? So what if my vector was the vector 1, 5? Now, since I don't have the same number of columns, 3 columns, with just 2 entries in the vector, 3 is not equal to 2, and so Excel knows that I can't multiply that matrix times that vector, because it's just not the right number of entries. Of course, if I, have another 3 entry vector, then I'm good. But if I have 3 entries in my vector and only 2 columns in my matrix, then oops, you have another issue. And so you have to have the same number of columns in your matrix and entries in your vector. Okay. So that's matrix-matrix multiplication. In matrix-matrix multiplication, though, the number of columns in your left matrix has to match the number of rows in your right matrix. And there's no typo here. This is actually correct. The way that I think about this is like I have this left matrix that has rows times columns. I say it's like a 3 by 4 matrix or whatever. And I have a right matrix which has rows times columns, So maybe this matrix is 3 by 4, and this matrix is 4 by 5. I have to have the columns on the left match the rows on the right. That just means these inner 2 numbers have to be equal to each other, right? Columns on the left have to match rows on the right. And then once I perform my matrix-matrix multiplication, the product matrix is going to have the same number of rows as the left matrix and the same number of columns as the right matrix. I know this is a ton of information, but like in this case, if I have a 3 by 4 matrix times a 4 by 5 matrix, the result is going to be a 3 by 5 matrix. So let me give you an example. If this matrix is 7 by 5, and this matrix is 5 by 3, then what are the dimensions of my product matrix?
7 by 3.
Yeah, it would have to be 7 by 3. And also, this works because 5 columns and 5 rows matches up. And so that is going to work for matrix-matrix multiplication. Okay? What if I have a 3 by 4 matrix times a 2 by 3 matrix? Then, for my product matrix, what are the dimensions of this product matrix?
Is that possible?
It doesn't work. Yeah, exactly. So that's a trick question. 4 is not equal to 2, so this is not defined. There's no way to multiply these matrices because the number of columns and the number of rows doesn't match. Excel knows this as well. So like here I have this matrix product AB. If I have 3 columns in A, then I have to have 3 rows in B for this to work. If I deleted one of the rows of B, it doesn't work. B times A should actually still work though. I say that B times A should work because there's 3 columns in B and there's 3 rows in A. So this should actually still work. I just probably need to adjust my formula. Yeah, there we go. So if I did B times A, now this is 2 rows and 3 columns times 3 rows and 3 columns. And so the 3 columns and the 3 rows works for B times A. And the product matrix should have 2 rows and 3 columns. And that's what we get, 2 rows and 3 columns, right? Okay. So the identity matrix, we're going to use a capital I to represent the identity matrix. And the identity matrix is a special matrix where for any vector v, I times V is equal to V, right? And it doesn't matter what V is. So just as an example, V could be a vector 1, 2, 3. And multiplying by the identity matrix should give me back the vector 1, 2, 3. So who can tell me what is this identity matrix? Yeah, this matrix has to be a matrix with 3 columns because I'm multiplying by a vector with 3 entries, or 3 rows, right? 3 columns times 3 rows works. Also, the product is 3 rows, 1 column, so I know that this matrix has to be a 3 by 3 matrix. You can think of this vector as being a 3 by 1 matrix, right? And the product has to be a 3 by 1 matrix. But this identity matrix is a 3 by 3 matrix. And the only matrix where this is true is this one. So the identity matrix has 1s on the diagonal. And it has 0s everywhere else. Identity matrices must be square meaning the number of rows has to equal the number of columns. And hopefully you can see why, right? If I'm multiplying times like a 3-dimensional vector, or like a size 3 vector, then the vector is like a 3 by 1 matrix, and I have to have a product which is a 3 by 1 matrix. And so the number of columns has to match 3 so that the multiplication even works in the first place. The number of rows has to match 3 so that your product has 3 rows. So identity matrices have to be square. But aside from being square, you can have an identity matrix of any size, right? So this is a 2 by 2 identity matrix. And then, of course, you could have a 4 by 4 identity matrix. Like that. But you get the idea. 1's on the diagonal, 0's everywhere else. And so yesterday, I keep referencing yesterday, but I'm not going to do any Gaussian elimination today because it just takes too long. Yesterday what we were doing is we had some augmented matrix, and then we did the Gaussian elimination algorithm, and then what we ended up with was the identity matrix augmented with my solution, right? We had some matrix vector equation, AX equals B, and we solved for X in the matrix vector equation by Gaussian elimination. We took in my augmented matrix, A augmented with B, did the algorithm, and then we ended up with the identity augmented with X. Let me open that up one more time. Just do a real quick one because I have Excel. Right. So this was a giant, how big is this matrix? 11 by 11, 11 rows, 11 columns. And then I had some B vector, which was an 11 by 1 vector, column vector. And then once I did Gaussian elimination to it, notice that this is the 11 by 11 identity matrix, right? There's 1's on the diagonal and there's 0's everywhere else. And then this would be my X vector. This would be my solution to that matrix vector equation. Okay. So some matrices have a property that we call invertible. Some matrices are invertible. Not every matrix is invertible, however. And by the way, invertible matrices must be square. So if you have like a rectangular matrix where the number of rows doesn't match the number of columns, then it automatically cannot be invertible. If you have a square matrix, it could be invertible, but it's not always necessarily invertible. If your matrix is invertible, if A is invertible, then we denote the inverse matrix with a little superscript -1. And we call it the inverse matrix of A. And A times the inverse matrix is the identity matrix. And the inverse matrix times A is also the identity matrix. So, like I said before, matrix-matrix multiplication is not commutative in general. If you've got just two different matrices, the order in which you multiply them really does matter. We saw that earlier with A times B and B times A. That gave us two different product matrices. But if you have a matrix with its inverse matrix, then only in that very, very, very specific case it is commutative, because multiplying a matrix with its inverse gives you the identity matrix. So, if you wanted to find an inverse matrix and you were lazy, what you could do is you could, let me just generate a random one real quick. The inverse matrix in Excel you can find by typing equals minverse, or M-I-N-V-E-R-S-E for matrix inverse. Open parentheses, you select the array, you close parentheses, hit enter, then you select the same size area, and then you go back and Control-Shift-Enter, and then that is the inverse matrix. So this matrix is square, so it can be invertible. There's a chance that you can end up with a matrix that's not invertible, even if it's square. So like this column says 3, 6, 9, but if I change this column to be 7, 9, 4, oh, I broke it. So this matrix is not invertible. But the original one I started off with was, so some square matrices are invertible, others aren't. This one is, because Excel found the inverse matrix for me. And what happens now if I multiply the two? Like I told you before, this should give you the identity matrix if I take these two matrices and I multiply them. So let's do this. And the identity matrix should have ones on the diagonal and zeros everywhere else. And this is another example of what I was talking about at the end of class yesterday, called round-off error. Since Microsoft Excel and Python and Visual Basic and everything else mostly uses double precision floating point variables to store this number in computer memory, in the process of doing all of this math, and it's a tremendous amount of math, along these operations you're always rounding off just a little bit. And in this case, that's a number really close to 0, but it's not 0, and that's a number really close to 0, but it's not 0. And so you have these issues whenever you take matrix inverses in general. So in any kind of computational math, with really big math problems, we try to avoid taking inverse matrices, both because it's computationally heavy and because you end up with round-off error problems like that. Okay. So back to our matrix vector equation. If I have this like I said, solving for b, if you know a and x, is really easy. You just do matrix vector multiplication. If I want to solve for x, I can either do the Gaussian elimination algorithm that we talked about, or what I could do is I could multiply both sides of this equation by A inverse, and then say, well, A inverse times A is just the identity matrix. And the identity matrix times this vector x is just going to be the vector x. And so this is one possible way you could use to solve the matrix vector equation, is you could actually take the inverse of the matrix A and then do matrix vector multiplication to do A inverse times B, and that should also give you x. And so this is a method that avoids doing Gaussian elimination, but you have to find the inverse matrix.
How to find the inverse?
I'll tell you that. Oh, I'm running out of time. I was planning on telling you that today, but I'll have to post it in a video over spring break, I guess.
Somewhere like a brief description.
Okay. Let's try to get to it. So you could solve this matrix vector equation using Gaussian elimination, where you augment A with B, and then you do that algorithm and you find the identity matrix augmented with X. Now, if I replace that X vector with the inverse matrix, then the equation A times the inverse matrix A is equal to the identity matrix. So instead of writing A augmented with B, what I'm going to write here is A augmented with, oh sorry, I'm down here. A augmented with the identity matrix, right? Because B is over here on the right side of the equals, now the I is on this right side of the equals. So I can write A augmented with the identity matrix. And then after I do this Gaussian elimination algorithm, what I should end up with is actually the identity matrix augmented with the inverse matrix. So this is actually the best algorithm for finding the inverse matrix, is doing the Gaussian elimination algorithm, but you augment your original matrix with the identity matrix before doing Gaussian elimination. So finding the inverse matrix is a lot more additional operations than just doing Gaussian elimination to solve your matrix vector equation. It's just making it a lot longer. It takes a lot longer to do solve. It requires more computer resources, and there's more opportunities for round-off error because you're doing more operations in general. So if I have A and I want to find A inverse, what I do is I take A and then I augment with the identity matrix. Now I'm going to do Gaussian elimination, and after I do Gaussian elimination, I should end up with the identity matrix augmented with a little 2 by 2 matrix that would give me the matrix inverse.